I thought I'd do a couple more complex rigid body momentum examples, and these are useful just to sort of look at um, rolling. I mean, generally it's rolling, and some of the more complex ideas associated with rolling. I find these problems, the ones I'm going to do, uh, are often the most challenging course problems just because they look at things a lot differently than what we're used to. And so intuition, again, and I can't say this enough, goes out the window. And please don't trust what you think is happening. Look very carefully at the motion and start to think about what's happening. So example one, a cord is wrapped around a spool and pulled vertically upwards. System starts from rest. What is the speed of the spool's center of mass after 2.3 seconds? What is the minimum static coefficient of friction to maintain rolling without slip? So you have a force F, which is acting upwards, and it's 200 newtons. You have a radius R, the inner radius over here, 0.5 meters, the mass of the spool, which is 83 kilos, and a delta T of 2.3 seconds. What is, and a radius of gyration of 0.3 meters for the spool. So you have the spool. And the first thing you do before you do anything, not assume anything, is just put in all of the forces. So if you start with that, you have the force which is acting upwards, which is what you were given. You have weight, which is acting downwards. You have force of friction, which is acting to oppose the motion. And finally, you have the normal force. So as usual, and I'm getting better and better at this, I have to put down what my coordinate directions are, and my coordinate directions are shown here. So x to the right, y upwards, and counterclockwise is positive rotation. So I start with linear conservation of linear momentum and conservation of angular momentum. So I have mvg x1 plus the force of friction equals mvg x2. So the center of mass is what I'm looking at. Finally, I have ig omega s1 plus time 1 to time 2 of force of friction times the inner radius minus force of pull times the inner radius over delta t, which is that 2.3 seconds. Ig omega s2 is the final rotational speed of the system. Ig I know because it's a radius of gyration, so it's mkg squared. And I also know that this thing starts at rest and has an initial velocity of 0 meters per second. I also know it's rolling without slip, which allows me to immediately write this relationship over here, which is vgx over r inner, negative, because that's going to be kind of what I assume the direction is going to be. It's kind of, if I do the vector calculations, it would be a little bit better in terms of showing that. But in terms of what I know, in terms of what the math will come out, that's what I expect. So I remove those terms and neglect them from my expression. I have then the integral of friction force over time is equal to the final velocity of the system. I also have the moment caused by the friction force minus the total force or pulling force times the inner radius times delta t. And that's equal to the final Ig omega, and Ig is mkg squared again. Omega is Vg over R, and I just substitute in terms. And you'll notice that as I'm doing these problems, I'm writing them out in variables. And when I write them out in variables and go through all of the steps and sort of multiply everything across, this is what I get. And finally, when I'm done with all of this, spool doesn't move in y, right? It doesn't go up or down, doesn't bounce. So n plus f equals mg. And so I can tell you what the normal force is, and the minimum force of friction required is going to be mu sub s times weight minus that pulling force. So substituting all the terms in, I know that mu sub Sn, mu sub S Fmg minus F delta T equals Fr squared delta T over R squared plus Kg squared. Put all the terms together, cancel all the terms that disappear. I end up with a relationship now for the minimum static friction coefficient. And you'll notice immediately that that delta T term doesn't play a role. It's gone. It canceled out. So it's only a function of the radius of gyration, the weight, and the pulling force. It kind of, again, I'm dangerous ground here, but it's kind of intuitive at this point. And I substitute in terms of 4.1 meters per second and mu sub S min, which is 0.24. Now, the nice thing about writing it this way is that I have written it all the way through with variables, and at this point in the problem, I'm just going to substitute numbers. So I've substituted all the numbers I was given at the beginning of the problem, and I got the result that I have here. That shouldn't be that difficult to do. If I had tried this with numbers, it would be a lot more difficult, and I'll explain why I'm beating this dead horse over and over here, because there's a reason. Example 2, what is the speed of the crate 2.5 seconds after release? The crate starts from rest. So an inner outer radius crate down at the bottom with the C on it, axial system XY and positive counterclockwise. The only tricky bit here is that the cord is wrapped around the inner and outer radius. The mass of the crate is given as 22 kilos. The mass of that pulley is 16. The inner radius is 8.2 centimeters. The outer radius is 19 centimeters. And K of that pulley is going to be 12 centimeters. So the radius of gyration is 12 centimeters. So if I do that, then what I have here is mass of the crate VCY1 plus integral 2t, T1 to T2, 2t minus the mass of the crate G dt, mass of the crate VCY2. Then I have IG omega big pulley, the integral of the two tensions, our outer, our inner, multiplied by tension, dt, and IG omega of the big pulley. And the nice thing about doing these things this way is I can write things like big pulley all I want and flip capitalizations on them. IG of the pulley is mkg squared. I have all of the terms here that I'm looking at, and I have a second free body diagram I want to make sure about, and that's this one, which is mcg 2t. So at this point I have 1, 2, 3, 4, which have defined various points on the pulley and on the second smaller pulley. I know that V1 equals V3 and V2 equals V4. And both of those I can relate to the outer and inner radius, but I know that omega of that big pulley is the same on both cords, or both sections of cord. I have 5 which I can define here, and 5 is going to be negative velocity of the crate in the J direction. So I know this is sort of rotating counterclockwise, it's dropping, and I kind of have to figure out what the velocity of this is, and it's going to be some sort of average. So let's continue with this. If I do that, I can say, well, look, V4, V3 are both attached to the same pulley, and V4 is equal to V5 plus omega pulley cross R4 with respect to 5. Velocity 3 is equal to velocity 5 plus omega pulley R cross 3, 5. Cross with R3 with respect to 5. So 3 with respect to 5, 4 with respect to 5 are equal magnitude but opposite sign. And so in order to do this, I'm going to say, well, with respect to 5, and I'll define everything with R3 with respect to 5, it's minus R pulley I. So I have all of those terms now. I can substitute the V of the little pulley equals velocity of the crate, because that's moving at the same rate, and it's going to be 1/2 V3 V4. Velocity of the crate times 2 is equal to omega the big pulley R inner plus R outer. Omega the big pulley is then twice the velocity of the crate divided by R inner plus R outer. So it's kind of difficult to visualize. It's really hard to visualize this, but it's one of those things that is actually kind of useful, and you've done some similar types of problems, and it's actually helpful to think about it in terms of the vector approach to solve through for this. And you then have velocity of the crate, omega of the pulley, 1 and you have velocity of the pulley, omega of the pulley 2, which you know is velocity of the crate 2 to our inner, our outer, times 2 in the k direction. So you got all of that, so not so bad. So substituting in terms and putting all of this together, putting my free body diagrams, there we go, and correctly writing my equations at the top before giving you the answer, I get 2t m crate plus vcy2 r outer plus r inner is t, the integral of the tension, twice the mass of the big pulley, kg squared velocity of the crate, and over r inner and r outer. Now delta t is the end to the beginning, so that's kind of given. So if I substitute in terms, mass of the crate g, r outer, r inner, quantity squared, delta t, for mass pulley, kg squared, mass of the crate, r outer, r inner, I'll get the second velocity of the crate is 15.66 meters per second. This is a hard problem. And in fact, when I did the first video, I copied this relationship to the second line because I just wanted to copy things quickly, and I forgot to remove a g. And so this is why I'm doing this video all over again. But one of the nice things, again, because I had written it in variable form, was it was a lot easier for me to pick out right away that I had made a mistake. If I'd written it as numbers, it would sort of disappear into the ether, and I'd never figure out what exactly I had done. By doing it this way and just systematically writing the variables out, you often find it's a lot easier to follow these problems. At least it is for me. Rolling problems are very difficult to visualize. In fact, I think that rolling, anything to do with moments, angular velocities, angular acceleration, are often very, very challenging, and you always need to solve them with a lot of really careful work, free body diagrams, kinematic diagrams, and you really have to break them up into parts.